talk to us. So Kazuharu Bamba is going to talk to us about his last presentation in this conference.
Yes, thank you very much for the introduction. I would like to talk about the review on the issue of dark energy and modified gravity theories. First of all, I would like to thank the organizers and especially the Professor David Momani to give me a chance to talk about this, my presentation. In this presentation, there are two parts. The first part will review the dark energy problem and the modified gravity theories, and the second part, I would like to introduce our recent work, the contents of which is the dynamical system analysis of Bianchi type 1 spacetimes in F over gravity. Let me explain the first part, a review on dark energy problem and modified gravity theories. It is known that the current expansion of the universe is accelerating. This is so-called the dark energy problem. This is supported by the type of supernovae observations. This is the supernova legacy survey data. The horizontal axis showed redshift and the vertical axis showed distance estimators. Yes.
Bamba, can you put the mic a little bit away from you? Just a little bit.
Okay. And is it okay for you?
No, it's a bit far.
A bit far. Okay.
Yeah, I think.
What about this one?
I think that's a bit better, because if you put it a little bit away, I think the sound will be less. I think that's fine. That's okay.
It's okay.
Yeah. Thank you.
Thank you very much. Okay. The flat lambda cosmology can fit the data well, better than the pure matter cosmology. This is a bioacoustic oscillation. The horizontal axis shows the separation in the covariant coordinate, and the vertical axis shows the two-point correlation functions. We have a few such oscillations. This is due to the large-scale structure of the universe. Combine the data of supernovae, VAO, and the cosmic microwave background radiations, we can see the fraction of dark energy and the fraction of dark matter for the case of the flat universe, like this point. It is known that the current three cosmic compositions are as follows. The dark energy about 70%, and dark matter is about 1 over 4, 25%, and the other matter, which is ordinary so-called baryon, is only less than 5%. To realize the current cosmic accelerations, the negative pressure, which is the pressure of the dark energy component, should be larger than the universal gravitation. This is very peculiar phenomenon, the mysterious. There are two main approaches to the dark energy problem. The first is a general relativistic approach, which is so-called the dark energy, with its negative pressures. The second is to extend the gravity theories. The gravitational field equation is given by these expressions. The left-hand side is the gravity sector, and the right-hand side is matter sector. The general relativist approach is to add the dark energy components on the right-hand side. The extension of gravity theories introduce the corrections of gravity sector in the left-hand side. The condition for the accelerated expansion is as follows. For the homogeneous and isotropic universe, the equation of the scalar factor A is given by this expression. If the A square dot is positive, it means the accelerated expansions. If the W uh, equation of state of the universe is given by pressure over energy density, and W is less than -1 over third, is this the condition for the accelerated expansion of the universe. The current W value is given by this valued by Planck data less than -1. This means that the current expansion of the universe is accelerating. We introduce the general relativist approach. There are several approaches in general relativity. The first is the cosmological constant. The second is the scalar field, like so-called X-matter quintessence. The phantom with the long sign kinetic term, essence with non-local kinetic term, tachyon from string theories. The third is the cosmic fluids. It is known that there are several candidates, such as Chaplin gas, which whose equation of state is given by this peculiar expression and the viscous fluid. The second, we explain the extension of the gravitational theories. In the literature, there are several proposals of the extension of gravitational theories. The first is the F over gravity. This is a we in the second part we concentrated on the F over gravity. The skeleton theories, including the Browns-Dickey theories, the Gauss condensates, and the higher order curvature term, such as the Gauss-Bonnet term, and the f of z gravity. Here, the current z is the Gauss-Bonnet invariant, and the digital brain wide scenario, and the f of t gravity. This is extended parallel Lagrangian density, described by the torsion scalar capital T and the teleparallelism with the Weisenberg connections. In teleparallelism, the theory is described by the torsion scalar capital T rather than the curvature in general relativity. And Galilean gravity. In this gravity, the equation of motion can be kept after the second order. This is very well-defined theories. And Holography theory, this is the generalization of Galilean gravity. And non-local gravity, this is a quantum effects and Holography gravity. And massive gravity and bigravity are known in the literature. Um, from now on, I would like to explain the one of the most famous modified gravity, F over gravity. The action is given by this expression. If F of R is exactly R, this is a general relativity. The gravitational field equations is given by these expressions. And flat, homogeneous, and isotropic background gravitational field equations is given by these expressions. And therefore, the effective equation of state parameter is given by these expressions. Actually, the cosmic acceleration can be realized in F over gravity. For the prototype F over R model, this is a double power model. If the scale factor is given by such a power type, here is Q is the given by this expression, then if the n is equal to unity, which is which leads to the Q is second, Q is 2, then the W becomes less than minus, W becomes the minus 2 over third, which is less than minus 1 over third. Therefore, such a prototype f over model, in such a model, the cosmic acceleration can be realized. Moreover, we demonstrate that evolution of the energy fractions. The horizontal axis shows the redshift. The vertical axis shows the energy fractions. Then we can see that in our universe, the matter is dominated, but in the late time universe, the dark energy components become grower and grower, and then the current universe, the dark energy components become dominant. In this is the case for the exponential gravity, which is the one famous model in F over gravity. Here, this one is the explanation of the notations. We explain the conditions for the viability of F over gravity. The first is F prime is positive. This is the positivity of the effective gravitational coupling. Second is F2 dash should be positive. This is the stability conditions. The third is that the F over should become the general relativity plus the cosmological constant for the large curvature. This is the existence of a matter dominant stage. The fourth is the stability of the late time digital point. The fifth is that the constraints from the violation of the equivalence principle, which is so-called the solar system constraints. And also we explain the viable F of R models. This is some examples. The first is Wu-Sawitzky model. The second is the Stravinsky's model. This is a very famous model. The third is the Tsujikawa's models with the tangent hyperbolic functions. The fourth is exponential gravity case, which has already been introduced in our previous slides. Let me summarize the first part of these presentations. We have explained the late-time cosmic acceleration, namely the dark energy problem, and revealed candidates for dark energy and modified gravity. Okay, let me move to the second part. As our recent work in modified gravity theories, I would like to introduce our recent work, the dynamical system analysis of Planck type 1 spacetimes in F over gravity. Now, this is the collaboration with the Professor Chakrabarty and the Professor Sa. In this work, we present a dynamical system analysis in terms of the new expansion normalized variables for homogeneous and isotropic Planck type 1 spacetimes in F over gravity and the presence of anisotropic matter. We demonstrate that the Einstein's equations are reduced to an autonomous 5-dimensional system of ordinary differential equations for new variables. We make the autonomous system analysis in vacuum for the power law form of f of r and show that the dynamical system can be solved exactly. We consider these actions and as a background, we suppose homogeneous and anisotropic Young type 1 metric like this. Here, beta denotes the quantities which characterize the anisotropies of the universe, and A is the average scale factor. We introduce the following relations like this one. Mm, In that case, the sigma squared, which is given by these expressions, means the total amount of anisotropy and the metric. Here, h is the average Hubble parameters. The scale curvature is given by these expressions. The energy momentum tensor of an anisotropic baryonic paratotropic fluid is given by these expressions. And an isotope equation of state is given by these expressions. And in that case, that omega is the average baryonic paratotropic parameters. Here, mu is given by these expressions. And in this setup, we can obtain the set of field equations, which is the four equations for H, low, and beta plus minus. The first is given by this one, and the second is this one. These two equations are corresponding to the Friedman equations. The third one is the equation for beta. Beta denotes the anisotropy of the universe. The first one is the so-called continuity equations. For the analysis, we introduce a logarithmic time like this one. And for the dynamical system analysis, we usually use the following dimensionless expansion normalized dynamical variables like this one, U1, U2, U3, U4 plus minus, and U5. In that case, the first Friedman equations becomes such a energy constraint, and the second Friedman equation and the equation for the anisotropy and the continuity equations becomes the five-dimensional system of autonomous first-order differential equations. These equations are given by these expressions. Here, the gamma is given by these expressions. I will explain the detailed expression for gamma later. The forms of f of r and the corresponding expressions of gamma are given by these expressions. The first case, the power law form of f of r, we can obtain the gamma is given by delta inverse. The second f of r form, like a logarithmic form, gamma is given by these expressions. And the exponential gravity case, gamma is given by U3 over U2. The prototype double power 4 law form of f of r case, the gamma is given by these expressions. And the general double power law form of f of r, gamma is given by this expression. If the A is unity and B is true, this is the Stravinsky inflation model. This is consistent with the recent Planck data. This is the Planck 2018 data. Horizontal axis show the primordial tilt, ms, and the vertical axis show the tensor to scalar ratio. Here is the Stravinsky inflation model. This is R square, which is so-called R square gravity. This is consistent with the Planck data. We explain the applications to cosmology of our dynamical analysis system, dynamic system analysis. The first, we consider the parallel form of f of r and the case of vacuum. In that case, U5 is exactly the zero. And in this case, we have these equations, and therefore we obtain the two-dimensional phase space form spanned by the variables U1 and U4 like this one. And therefore, we can do the dynamical system analysis for these two parameter spaces, two parameter space. And this is the result of this case. The horizontal axis showed U1, the vertical axis showed U4. And this line is the invariant line. So we can see that here, 0, point is the stable fixed point. Now this is case for the delta is exactly unity. This means that this is the R square gravity, the so-called Stravinsky inflation model. And this 0, fixed point leads to the de Sitter solution. This is a stable one. We can see that the vacuum solutions in the case of this parallel form, namely the U5 is exactly the arrow. This is a vacuum case. These solutions can be solvable, and especially for the case of delta is exactly unity. This is the R square gravity. The stable fixed points corresponds to the de Sitter solutions. Now this is the solution of Stravinsky inflations. In this case, the scale factor, average scalar factor A is given by these expressions, the exponential form of HT. And this result is consistent with the past famous literatures, references. In that case, the R is given by these expressions, and from the energy constraint, we can obtain such a simple differential equations. And we can find that the unique solution of this simple differential equation is given by this expression, namely the f of r should be proportional to r squared. And finally, we can find that the case of R squared is unique among all vacuum f of r theories with respect to the existence of the digital solutions with an arbitrary H. Excuse me. This is consistent with the past studies. Our new point of this study is that these results can be reduced in a systematic way and the dynamical system analysis. This is a new point of this work. And that this is the case of delta is 1 over 10. The horizontal axis shows the U1 and the vertical axis shows the U4. We can see that this is the invariant line, and we have the fixed point here, minus 3 over 2 and the L. However, this fixed point is not an unstable one.
What is U1, U2, U4? Sorry?
excuse me. Yes.
What is U1 and U4?
Okay. U1 and U4 are given by this new U1 is such a
Okay, I see.
combination, and U4 is like this one. U4 is a little bit related to the anisotropy of the universe.
Okay, yeah,
Yeah.
thanks.
No, no. Okay. So in the for the case of 10 delta is 1 over 10, we have no stable fixed point. This is fixed point, but the unstable one. Here, there is an attractive and here is an attractive and a repulsive segment located respectively above and below this depicted point, the minus 1 over 2, 1 over 2 here. The, in the case of delta is not equal to exactly unity, then we have these expressions, and therefore the form of h is given by these expressions. If the, the large delta is positive, which means that the small delta are given by this regime, then we can have a big leaf singularity. And if the large delta is negative, which means that small delta is given by this regime, we can obtain the parallel expansions in terms of h. Um, Next, we show the case of f of r is given by the parallel form and in the present in the in the presence of anisotropic matter. In this case, the autonomous system is given by these differential equations. Here, since we consider the anisotropic matter existence, the U5 is not exactly the error. This U5 is a finite value. After our analysis, we can find that the four isolated fixed points, the solution with U4 plus and U4 minus are the error, namely the following values for the pair U1, U3. We can obtain these pairs. Finally, we can find that in the case of with the anisotropic freeze, all isotropic fixed points are unstable, which means that there is no asymptotically stable isotropic solutions in the presence of anisotropic matter. And this point is also realized for the case of exponential gravity. Uh, we can find that the same results can be seen in f of the exponential gravity. Okay, let me summarize the second part. Our recent work, we have analyzed the cosmological solutions for the homogeneous and anisotropic Planck type one spacetimes in f over gravity under the existence of anisotropic matter. It has been demonstrated that the Einstein's equations are reduced to an autonomous five-dimensional system of ordinary differential equations for new variables. By making the autonomous system analysis of the vacuum solutions for the parallel forms of f of r, we have shown that the dynamics can be solved exactly, and that only for the case of r squared there exists a stable digital solutions, which is the so-called the solutions of the Stravinsky inflation. Thank you very much. Okay, let me stop my presentation.
Okay, thank you for your presentation. It was nice and really, it was like a summary of what is going on. And thank you very much.
Thank you very much.
I have